Greetings and welcome, Mr. Waddy here, and today we're looking at some resources and problems from All Things Algebra, Algebra 2, Unit 3 about linear programming. And so I've got a bunch of terminology and a process here, which these words and phrases won't make a lot of sense until we jump into the examples, but here we go nonetheless. Linear programming is the process of optimizing, right, finding the best possible solution of a linear objective function. So that might be like maximizing profit, minimizing cost, minimizing material use, something like that. Subject to a linear system of linear inequalities called constraints. And so constraints are like real-world limitations, like x has to be less than 40, where x would be the number of hours someone works in a week. And so we might have a variety of constraints defined in terms of our variables, and then we try to optimize a function based off of that. Optimization is the process of finding a maximum or minimum value, and the graph of the system of constraints is called the feasible region. And so there's a whole bunch of different XY combinations, but some of those combinations just might not work if they go beyond any one of those inequalities. And so the process in general is going to be, I'm going to use the constraints to write a system of inequalities. I'm going to graph that system showing the feasible region. I'm going to write the function, objective function, whether I'm trying to maximize or minimize, and then I'm going to test the vertices. All right, and so in the feasible region, because it's going to be some polygonal shape, I'm going to find all of the vertices, or the corners of that shape. And then I'm going to plug those xy coordinates into the objective function and seeing which one gives me the best result. All right, so that's a whole bunch of new language, but let's jump in and look at an example and see how this goes. So here's example one. Let's see, I'm going to use green first. The first thing I'm going to do is define my variables and then use those to write constraints. And the majority of the time, for word problems, the variables are going to be found in the question that's being asked. How many first class and tourist class tickets should they sell? And so I'm going to let x equals the number of first class tickets. Man, I might not have enough space. I'm already writing so large, I feel. And y will be the number of tourist class tickets. Boom. And now we're going to define some, or we're going to write constraints using these variables and some of the facts written within this problem. So let's read the problem. The smallest plane in the coast-to-coast airlines fleet offers first class and tourist class seats and can hold a maximum of 50 passengers. And so max of 50 passengers. So I'm going to write this constraint as the passenger limit for constraint. Boom. And so the number of first class tickets and the number of tourist tickets has a maximum of 50. And so I'm going to write x plus y has got to be less than or equal to 50. You can't sell more tickets than that. And what we'll do with this is we're going to end up graphing this inequality. And so tell you what, let's subtract x from both sides. So I'd get y is less than or equal to negative x plus 50. And we're on a roll here. We'll start graphing right away. So here's 48, here's 52. So 50 is right in the middle. And the slope was, scroll up so you can see it, -1. And so it'd go down 1 over 1, down 1 over 1, etc. It would end up intersecting again over here at 50. Let's see, I got my line tool. Oh, wonderful. And so I'm going to graph this inequality. And so this is less than or equal. And you might remember from Algebra 1, the equal part tells me it's going to be a solid line. And less than means I would shade this underneath. Okay, and so I guess I'll lightly shade this here. Something like, boom. All right, let's keep going. Back to the problem. And let me grab my... Ooh, I usually use purple for equations. Yeah, that'll do. That'll do. In order to charter a flight, the airline must sell at least 8 first-class tickets and at least 20 tourist-class tickets. So that's actually 2 separate constraints. So I'm going to say, I'll call this min ticks. Boom. And so I have the number of first-class tickets, X, must be at least, so greater than or equal to 8. And the number of tourist tickets, Y, must be at least Y is greater than or equal to 20. And so I could have made that 2 separate inequalities, but X is greater than or equal to 8 is going to be the equation of a vertical line. Boom, I remembered the little double tap trick to make it horizontal or vertical. And so X is greater than or equal to 8. The equal part tells me it's a solid line rather than a dashed line. Woo. And here we go. Let's see, actually, so if I shade this, it would be shaded this way. And you remember graphing systems of inequalities from Algebra 1, I'm sure. And so the overlapped shaded region is the common region of possible solutions. And then Y is greater than or equal to 20. Ah, Mr. Walte, rolling the wrong way. All right, let's make this horizontal and at 20. And tell you what, I'm going to change this to... I'm going to change it to orange. And greater than or equal tells me it's solid. Greater than would mean shade above. And so right now that looks pretty nasty. But the enclosed common region is this region right. All right, and so this is called the feasible region. Okay, and let's verify. I don't believe, and then it talks about profit. We'll get there in a second. All right, so this is the feasible region where any point in that green area will satisfy the constraints of all 3 of those inequalities. Okay, and I'm going to be interested in vertices. All right, and so let's find those vertices. So this is one is 8, 20. Another is looks like 8, ooh, now I'm tempted to say 42. Let's see, if X is 8 and I plug 8 into the blue line, yeah, I'd have negative 8 plus 50. It is 42. So 8, 42 is another one. And this point, it looks like it's 30. Or actually, oh, I know Y is 20 for that orange line. And if I plug in 20 for Y and then subtract it from both sides, yes, X is 30. So 30, 20. And so while any point within this region would work, the vertices, the corners, are going to be the ones that have the potential of giving me an optimal solution, okay? And so any combination in the green area would work. So like, let me get the x-axis in view here. So 16, 24, that point could work. It's not going to be optimal though, all right? So let's see, let's figure out, now I've got those, let's write the objective function. And so the company makes $40 profit for each first class ticket and $30 profit for each tourist class ticket sold. In order for the company to maximize its profits on a single flight, how many of each should it sell? And so my profit equation is defined in terms of those xy's. And watch this. So I'm going to write, watch this function notation. Instead of p of x, it's p of x comma y is going to equal Oh dear, I gotta keep scrolling back. Here we go, $40 for every first class ticket, so 40 times X, and $30 for every Y, for every tourist class ticket. And so here's the profit equation that I want to optimize, the objective function. And so what I'm going to do is plug in these coordinates, X and Y, for each of these and figure out which one will give me the optimal outcome. And so let's see, 40 times 8 plus 30 times 20. So that's what, 320 plus 600, I believe is 920. Over here, then I'd have 40 times 8 plus 30 times 42. And let's see, I'm actually gonna... Here we go. Realizing I don't have my calculator on hand. All right. I've known far too long that I make mistakes making videos. Well, 40 times 8 is 320 again. And then I've got this Desmos tab open. Oh dear. 30 times 42 is 1260. Plus that 40 times 8, 1580. And so this one's a pretty good candidate, right? That's definitely more than the 920. So 1580. And now let's try this combination. This one's got a shot. This one's got a shot. So this would be 1200 plus 600 is 1800. And so this one is the best combination right there, 30 comma 20, right? This point right here. And so that's the combination that would maximize profits for the airline. And so let's now write the solution. And so what does 30/20 mean? Well, 30 was the X, the number of first class tickets, and 20 was Y, the number of tourist tickets. So let's I'll write that in green. Why not? And so they should sell 30 first class and 20 tourist. All right. And the maximum profit, by the way, is $1,800. Okay. And so let's go back to just what this was, right? We defined our variables. We wrote constraints as a set of inequalities, a system of inequalities. We graphed those things. We wrote an objective function that we were trying to, in this case, maximize, although I could have been trying to minimize it. And then I took the vertices, the corners of the polygon, the feasible region, plugged those in, and figured out which one gave me the most. So let's keep going. Here's a couple more examples. Let's see. Natalie is a hairstylist. When making appointments for her clients, she allots for 30 minutes for each cut and 2 hours for each cut and color. She has 10 hours available for appointments per day and prefers to see no more than 8 total clients. Each routine cut costs $40, and so these are costs. Okay, well, all right, costs to the customer. So that's what she charges. So she's going to try to maximize her income. Gotcha. All right. So let's define our variables. How many of each type of appointment? And so let's say X is what was the first one that showed up? Cut and color. So cut only, and Y is cut and color. And let's see if we can identify some constraints. And so looking here, she allots 30 minutes. Okay, so this is a time constraint for each cut, 2 hours for each cut and color, and she has only 10 hours available each day. Okay, so this will be, I'll describe this as our time constraint, And I could choose to work in all minutes or all hours, but I'd rather not write it using both. If I use hours, I'd have to convert 30 minutes to be 0.5 hours. So I don't know, we'll just, Now, actually, based on my equation, my axes here that I'd already picked, here's the x-axis. It's only going up to 8. I'm assuming that's in hours. Yeah, based on what I'd written earlier. So let's use hours. So I'm going to write for my time equation 0.5x plus 2y equals 10. Or, not equals 10. That's the most she wants to spend. So I'm going to say is less than or equal to 10. I could rearrange this in slope-intercept form, although just plotting using intercepts is actually pretty effective for this. If I plug in 0 for x and solve for y, I would get 0, 5. If I plug in 0 for y and solve for x, I would get, this would be 0, divide both sides by 0.5. I would get x equals 20. Oh dear. All right. Wait a minute. Yeah, my graph is not helpful. And it's unrelated to... No, it shouldn't have been related to time. Huh. All right. Oh, you know what? It probably ends up... Well, we'll write it this way. It probably ends up not going over that far. That's okay. We'll fix it later. So let's see. Let's also rewrite this in slope-intercept form in case that helps. So if I subtract 0.5x from both sides, divide both sides by 2, then I would have had y is less than or equal to 0.5 divided by 2 is 0.25, negative 0.25. So I could call that negative a fourth x, and 10 divided by 2 is 5. All right, so there's one of those. This one will be a little bit easier to graph. So y-intercept is 5, and because both of the scales match, I can do the equivalent of just going down 1 over 4, down 1 over 4, and hopefully I've given myself enough room. I won't see where this line crosses the axis. This one is less than or equal. The equal part tells me it's solid, and I would shade below. And sometimes I just kind of like put a little arrow so I remember, so that way my graph looks a little bit less ugly, all the shading. Let's find another constraint. All right, she prefers to see no more than 8 total clients. So this could be our client. So the total number of cuts and the total number of cut and color, if I add those together, I want it to be less than or equal to 8 clients. If I use the intercepts method, plug in 0 for y and solve for x, I would get 8 and 0. If I plug in 0 for x and solve for y, I would get y equals 8. So 0, 8. And so sometimes those are the easier ones to graph. In this blue case, I didn't leave space for the other intersections. So, but look, if I plot those 2 points and just connect those, it's the same thing as if I had the, y-intercept of 8 and a slope of -1. Same difference. Okay. And so this was a solid line because it had the equal part and it's shaded underneath. Now, one of the things that I'll also point out is that by default, I also technically had these two constraints. X is greater than or equal to 0, and y is greater than or equal to 0. Technically, I have a line here. And the same one technically was true in the other situation. It just ended up not needing to be true because there was more constrainty constraints. But I can't have negative haircuts or negative haircuts and colors. And so if I combine all of these, and so, yeah, since I can't have negatives, that's why it's got to be more than 0. Can't be negative. And so if I combine all of these, the end feasible region ends up being this. And these are the vertices, the corners that I'm interested in. And so, tell you what, I'm going to write those down right now. So I've got 0, 0. So that would be 0 haircuts, 0 cut and colors. That's if that's her situation, then she should shut down her business, because that wouldn't be a good combination. If we optimized her income and we found out, you know, don't do any work, that's not a good situation. We've got 4, 4. And the last one is 8, 0. And it's not a bad idea to kind of think about these scenarios. So 5, 0, or no, I wrote that one wrong. 0, 5, guys. And then the 4, 4. So 0, 5 would be if she only did cut and colors. 8, 0 would be if she only did haircuts, right? And so even this sort of optimization could inform kind of her business decisions, whether she stops doing one of those things or charges more money, right? Something like that. So let's see, cut only costs are $40 and cut and color costs $100. So maximize her income. It's, yeah, technically revenue. They use the word income, so I'll write a capital I. So I of x comma y is equal to, so she's making 40 for every x and 100 for every y. So this is the objective function, and I'm trying to maximize it. I want the largest possible to come out of this. And so let's plug in these vertices and see what happens. So you can probably guess what happens when we plug in 0. I get 0 income. Not a great scenario. If she does no haircuts and 5 cut and colors, that would be $500 coming into the shop. Here's the one where she's got a combination of each. So this is 160 plus 400 is, $560. So right now, that's the winner for the moment. Or there's just 8 haircuts. And that would be $320. And so the best case scenario is the 4, 4 right there. And so 4 haircuts, 4 cut and colors. So she should do 4 haircuts, 4 cuts, cut only, and 4 cut and colors. Boom. And now technically there are other possible combinations. Like this is a possible combination, right? 6, 2. This is a possible combination, 7 and 1. But those will not be optimal, okay? The vertices are the ones that are going to give you the optimal scenarios. So that's a possible combination, just like doing 4 and 2 is a possible combination. It's just not going to be the optimal amount. Now, there is a rare scenario where if 2 of these tied for optimal, then that whole edge between them would be optimal. That doesn't happen very often. Who knows? Maybe it'll happen in this example. Last example, baking. Let's see, how are we doing for time? Meh. Been a little minute. Here we go. Let's keep going. Baking tray of chocolate chip cookies takes 3 cups of milk and 2 cups of flour. Baking tray of oatmeal raisin cookies takes 1 cup of milk, 4 cups of flour. Baker has 9 cups of milk and 16 cups of flour available. Makes profit. How many trays of each type of cookie should be made to maximize profit? And so X, it was how many of each type of cookie. So X would be the number of like chocolate chip trays. And Y will be the number of oatmeal raisin trays. And so those are my variables. Let's see if we can define some constraints. So in this case, each of these they consume some number of resources. Let's see, we've got 3 cups of milk for the chocolate chip. And well, yeah, let's think of our milk constraint. Be one of them. And 1 cup of milk for the other, and they have a total of 9 cups of milk. So this one I've kind of had to piece my clues together. So 3 cups of milk for every chocolate chip tray, 1 cup of milk, 1Y, for every oatmeal raisin tray, and there's a total of 9 cups of milk, and so you can only use up to that amount, so less than or equal. We could find vertices, or we could do slope intercept. If the numbers were really crazy on my grids, like if I was going up to, past 100, then intercepts is a great way. But slope intercept form's fine too. So I could also have rewritten this as y is less than or equal to negative 3x plus 9. Let's graph it that way. So here y-intercept is 9, and then down 3 over 1, down 3 over 1, down 3 over 1. That's fine, that's fine. Oh dear, I got rid of my blue. And so, here's my ruler tool. I'm just going to graph these. It's going to be solid because it included equality to that. And this was our milk constraint. You can't use more milk than that set amount. And so the number of batches uses up different amounts of milk. Boom. All right, our next constraint was flour. So chocolate chip uses 2 cups of flour and 4 cups of flour for every tray of oatmeal raisin cookies. And they have a total of 16 cups of flour available. And so this is our flour constraint. And so I'll do 2x plus 4y has to be smaller than the amount of flour that you've got. And so, yeah, I could do slope intercept form on this. So I'd subtract 2x from both sides and then divide by 4. I would end up getting y is less than or equal to negative a half x. The 16 divided by 4 is 4. And so y-intercept is at 4. And I'm going down 1 over 2. Down 1 over 2, down 1 over 2, down 1 over 2. And then draw my line. I've got to scroll down. Funny, it won't let the ruler tool get any closer. I'm going to end up having you guys do some of these on Desmos, which is even easier because you don't have to graph by hand. And so this is less than that. So that's the amount of flour available. And there are also some constraints as far as you can't make antimatter chocolate chip cookies. That's just a thing. And so I can't have negative number of cookies that I'm making. And I can't have a negative number of, oatmeal raisin either. And so these have to be greater than and greater. And so my feasible region, the common shaded area, in this case happens to be down in this corner. Now, it's not always going to be down in the corner touching the origin. It's possible it could have been one of these triangles as well, just so you are aware. And so the vertices, the corners of that, are what I'm interested in. By the way, if this corner didn't land nicely on a lattice point on the grid, then I might have to use the purple and blue equations and solve a system of equations. But you know how to do that, don't ya? Don't ya? So 0, 0 is a combo. 0, 4 is a combo, 2, 3, and lastly was 3, 0. And so I'm not interested in 8, 0 because that's using up more milk than I had available. That wasn't a possibility. All right, and what are we trying to do? Oh, they make $2.50 in profit per tray of chocolate chip and $2 of profit per tray of oatmeal raisin. How many of each type to maximize profit? And so I'm going to write 2.5x plus 2y is my profit equation, p of x comma y. And so I want to maximize that, right? And so we're gonna plug these in. So 2.5 times 0 plus 2 times 0. Yeah, you don't make any cookies, you're not making any money. Nope. Cookie clicker. Here we go. 2 times 4, 8. 2.5 times 2 plus 2 times 3. So that's 5 plus 6 is 13. And then 2.5 times 3 plus 2 times 0, that's what, 750. And so, boom, there's your optimal. So it's a combination of both. Not always the case, I want to point out, okay? And so, and also like, this sort of activity could end up informing different decisions. Like, oh, you know what? If I bought more milk, maybe I'd be able to make a whole lot more. You'd be able to, figure out what combination of changes in those variables would make the most sense. Those constraints, actually, in this case. So, optimal combination. Make 2 trays of chocolate chip and 3 trays of oatmeal raisin. And hopefully, the number of hours that it takes you to make that is worth $13 to you, right? That's another thing to consider, right? So anyways, so this is how to do system of equations work. Word problems, you got to define your variables, write some inequalities, graph those things, objective function, find your vertices. So that's kind of the systems part. And then plug those in, figure out which one of those maximizes. All right, well, thanks for watching, Internet friends. Have a great day.